Hello students, in this session we are going to discuss about vibrometer and accelerometer. In our regular classes we have completed the different types of sensors that we will see the list here. So sensors classification we have seen in our regular class, static and dynamic characteristics in our regular class, types. So we have classified them into proximity and inductive type, capacitive and optical type, displacement and temperature type, infrared and ultrasonic. Also we have discussed about RFID type of sensors, optical encoder, magnetostrictive sensor. This also we have discussed in our regular classes. Then in today's class we are going to discuss about vibrometer and accelerometer. These two are seismic type of instruments which are used to measure the vibrations of any body. So it is related to earth. So earth forces, gravitational forces are also plays a role here. That is why these are called as seismic devices or instruments. And then we will discuss about LVDT, strain gauge and piezoelectric type of sensors in next session. And the last one we are going to discuss about diaphragm, capsule and bellows, which are the devices which are retrofitted to pressure transducers, or we can retrofit to different devices like LVDT, strain gauge and other devices that we are going to discuss in last session of this unit. So now we are going to discuss about vibrometer and accelerometer. So now the instrument, vibration measuring instruments, these are the two types we are going to discuss in today's session. So the instruments which are used to measure the displacement, velocity or acceleration of a vibrating body are called vibration measuring instruments. So these are the instruments which are exclusively used to measure displacement, velocity or acceleration. So these are the three what you call terms which are differential terms. If you differentiate displacement, you will get velocity. If you differentiate velocity, you will get acceleration. So these are differential terms of a vibrating body are called vibration measuring instruments. So these are special purpose instruments. Vibration measuring devices having mass, spring, dashpot. So these are the three basic elements of any mechanical system are known as seismic instruments. So seismic instruments which are related to the ground. So ground and gravitational forces acts on the body and they are considered here. The forces which are due to gravity, they are also considered here. The quantities to be measured are displayed on a screen in the form of electric signal which can be readily amplified and recorded. So the quantities that we measure through mass, spring and dashpot, so they are readily displayable on the screen or which can be recorded also and after amplification. So that is nothing but signal conditioning. That's we have discussed in our regular classes. The output of electrical signal of an instrument will be proportional to the quantity which is to be measured. So here the output is directly proportional to the quantity which is being measured. So these vibration measuring devices can be classified into two groups. One is vibrometer, another one is accelerometer. So two types of seismic transducers are known as vibrometer and accelerometer. These two are widely used in any practical applications. A vibrometer or a seismometer, it is also called as seismometer, is a device to measure the displacement of a vibrating body. So displacement of a vibrating body can be measured using the vibrometer or seismometer. Accelerometer is an instrument to measure the acceleration of a vibrating body. The vibrometer is designed with a low natural frequency and accelerometer with a high natural frequency. So here the vibrometer is designed with a low natural frequency only, and accelerometer is designed with a high natural frequency. So vibrometer is known as low frequency transducer and accelerometer as high frequency transducer. So what is a high frequency transducer? You have to answer about accelerometer only. So please be careful with these terms and terminology. So vibration measuring instruments or seismic instruments operate on the principle of relative motion between a vibrating body and an inertial mass. These devices are commonly used for measuring displacement, velocity or acceleration of vibrating systems depending on the mechanical and electrical configurations employed. So for analytical purposes, the vibrating body is assumed to undergo the simple harmonic motion, that is nothing but SHM, which can be mathematically expressed using this equation: y small y equal to capital Y sin omega t. So here the y is the displacement of the vibrating base, so that is in terms of m meters. Y capital Y is amplitude of base vibration, it is also in terms of meters, and omega is the angular frequency of vibration, radians per second. So this is the simple harmonic motion equation: small y equal to capital Y into sin omega t. So next equation of motion. Here this is a setup, spring mass damper setup. You can see this is spring, and K is the spring coefficient, whereas m is the mass, and C is the damping coefficient. So it is attached to the frame, and you have scale. On the scale, the displacement of mass can be measured, and the displacement is in terms of plus x and minus x. Considering a seismic system with an inertial mass, so that is m, spring stiffness k, and damper with the damping coefficient C, the equation of motion of the mass can be expressed as m x double dot, that is the second order differential, and C into x dot minus y dot plus k into x minus y. So this is second order. The m is with second order differential, whereas C is with single, that is first order differential, and this is the zeroth order differential, that is equal to 0. X is absolute displacement of mass, and y is the displacement of vibrating base, and x dot and y dot are absolute velocities, absolute and base velocities, and x double dot and y double dot are accelerations, absolute and base accelerations, that is in terms of meters per second square. Now we can also find the relative displacement. The relative displacement between the mass and the vibrating base is defined as z equal to x minus y. So z is equal to x minus y. This is y here, so this is y, and we have m, and we have x, and x minus y, so that is z, and that is the relative displacement with respect to base, and it can be measured in terms of this. X is directly proportional to y plus z, so x equal to y plus z, so we can measure the displacement here with the help of y and z also. So next is accelerometer. So here the accelerometers are sensing transducers that provide an output proportional to acceleration, vibration and shock. So shock is also one of the measurand that should be considered, factor that should be considered. Measures all external forces acting upon the moving bodies, so that should include gravity also. Then only this can be called as a seismic device. One important factor concerning the accelerometers are sensitive to all external forces acting upon them. So accelerometers are sensitive to all the forces they are acting on the accelerometers. Accelerometers use one of the number of different mechanisms to transduce external forces into a computer readable signal. An accelerometer is a single degree of freedom device. So it is having one degree of freedom, single degree of freedom device. It has some type of seismic mass, sometimes called as proof mass, a spring-like supporting system, and a frame structure with damping properties to obtain inertial acceleration due to motion alone. So the inertial acceleration is actually due to motion only. Gravity must be subtracted, so gravity should not be considered. And if we see the setup, so this is the setup. So mechanical model of an accelerometer and a free body diagram of mass. So this is the free body diagram, FBD, of mass principle. So here this is the free body, FBD, and this is the mechanical setup. And here you can see spring, mass, and damper. And this is the x naught is the displacement of mass through spring. So K is the spring coefficient, and this is the damper. For that, this is the free body diagram. So Kx is acting in this direction against the x displacement. So x is in this direction is considered to be positive, and in this direction it is considered to be negative. So here b dx by dt, whereas m is the mass, d square x by dt square plus b dx by dt plus kx equal to m d square y by dt square. So this is the second order differential equation from this single that is free body diagram. So here the mechanical, thermal, and electrical analogies here I wanted to present. And mass is F equal to m dv by dt, and it's the equivalent thermal element is thermal capacitance, Q equal to C dt by dt. And whereas in electrical it is inductor and capacitor, and for spring it is capacitance in case of thermal as well as in case of electrical, capacitance and then inductor. So first inductor comes here for mass and then capacitor, whereas here for spring capacitor comes first and then inductor comes next. So damper is always a resistor. So resistance in case of thermal also it is resistance, and in case of electrical it is resistor, and V equal to R into I, and R is resistance, I is the current, and I equal to 1 by R into V. So these are the analogies in terms of electrical and also in thermal. And types of accelerometers and classification we can see here. So types of accelerometers, the force, so that is actually in terms of strain. So piezoelectric accelerometers and piezoresistive accelerometers, resonators. So these are the three types of strain type accelerometers. Force type, so strain is considered here, and under strain these are the three types of accelerometers. So in piezoelectric we know when the force is applied on any piezoelectric material, the EMF is produced, and that force acting on the piezoelectric crystal can be considered as an accelerometer. And in terms of displacement, potentiometric accelerometers, capacitive accelerometers, inductive accelerometers, servo controlled accelerometers, and optical accelerometers. So these are the different types of accelerometers. These are classified under strain as well as under displacement. So piezoelectric class accelerometer, we will see one example here. So piezoelectric accelerometers are self-generating devices characterized by an extended region of flat frequency response range, a large linear amplitude range, and excellent durability. So that is piezoelectric accelerometer, and these inherent properties are due to the use of piezoelectric material as the sensing element. So piezoelectric crystals can be used as sensing materials here. Piezoelectric materials are characterized by their ability to output a proportional electrical signal to the stress applied to the material. So stress is applied, so a force is applied on the piezoelectric material and the corresponding electrical output is generated, electrical signal is generated. A small mass can be positioned so that it is only supported by the crystal, and as the forces cause the mass to act upon the crystal, this induces the voltage that can be measured. So the induced voltage can be measured, that is directly proportional to the force applied or the acceleration that it generates. So here this is a simple setup, and this is the piezoelectric crystal, and it is kept by a mass and a housing, and it is within the spring. A spring is enclosed here, so this keeps the piezoelectric crystal under this mass. So this is a simple type of piezoelectric accelerometer. You can explain this for 5 marks. It is a 5-mark question. Applications or uses from these two devices can be to measure the constant or varying frequency acceleration, such as automobile braking. In automobile braking it is widely used, and elevator ride quality. So even in lifts or elevators it is used, and even the gravitational pull of the earth can be measured. The gravitational pull of the earth can be measured using these instruments. So these are the accelerometer and vibrometer, and you can explain and remember those equations. The derivations and all are not required at this moment for your syllabus. You can just remember those equations and try to explain the spring mass damper system in our own words. And references: Dioplin, measurement system applications and design, and Patronibus, sensors and transducers. You can always refer these two books for this content. Thank you, students. We stop here. We will meet again in next session. Thank you.